In this video, we will be learning how to work with multiple residuals in one different instance. So the first part A, says verify that a linear model appropriately models the data and state the equation of the linear model. So over here, the R square value of the linear model is a 0.55 approximately, and the residual graph checks out and looks fairly normal, so we can say that this can appropriately model this data, and the equation for that, for the linear, would be this listed right here. So, moving on to part B, the next day's time is 34.30 minutes. Predict the professor's pulse rate. His actual pulse rate was 152. How accurate was your prediction? So it gives us the x value, the 34.30, to plug in to our equation that we just got, our linear equation. So we plug that value in and we subtract it from our total value as our equation says, and we come out to a predicted value, a predicted pulse rate value of 147.3990, and the actual, as it said in the problem, was 152, and this is a pretty good prediction for the pulse rate. And so our prediction was fairly accurate, and I think can fairly well represent what the actual data was. So moving on to part C, suppose you were told only that the pulse rate was 152. You now want to predict the swimming time. Find the equation of the least squares regression line that is appropriate for this purpose. What is your prediction and how accurate is it? So we have to find the equation that is the most appropriate for this set of data. So looking at all the options, a logarithmic regression line would be the best for this set of data, and it has an R squared value of 0.5574, which was more than our linear. So this would be the most appropriate, and the residual plot of it checks out better than the of the linear. So this would be the most appropriate equation or regression line, type of regression line to use for this calculation. So this is the formula that we get for our logarithmic when we do that regression, and it tells us that we have a pulse rate of 152. Now our pulse rate, that is our y value. So instead of plugging it in for our x value, we have to plug it into our y value this time. So when we do that and plug it into our y value here, we have to subtract this initial value, this 1,000, and that'll give us our negative 1,195. And then we have to divide it by what we were going to multiply our natural log of x by. So we divide that, and that'll give us a positive 3.52, and then we're left with our natural log of x. Now to get rid of this natural log of x, we have to e both sides. So we do that, and that cancels out the natural log of x to leave this x by itself, and that's what we're looking for. And so 3.5215 e'd, you could say, is the predicted x value of 33.8384. Now this value is our predicted time that we're going to do that'll take to reach this pulse rate. Now our actual time to get to 152 is 34.12. Now this is only about 0.2 seconds off when you're talking about 34 seconds. That's pretty accurate of a prediction for the time for this value. It's a pretty close, it's a very good representation of the actual. So now to explain why, now the last question explain clearly to someone who doesn't know statistics why are there two different regression lines. So there are two different regression lines in this problem because those two lines strongly fit the graph. But the logarithmic one that we used in part C has the strongest correlation in the graph, so that's the one we used for that graph instead of the linear. The linear is still a strong fit to the graph, but the logarithmic has a stronger correlation, so that's why we used it in part C. So now we understand how we can use multiple regression lines in one problem and understand why we use regression lines, or the stronger correlated ones, in certain situations.